네, 안녕하십니까. 저는 IBM 정찬스입니다. 한국말 잘 몰라서 죄송합니다. 그래서 발표를 영어로 해드릴게요. My name is Charles Chung. I'm from IBM. I work as part of the applications team there. The picture you see here is of our IBM System 2. If you've never seen our quantum computer, that middle cabinet is where the quantum computers are. We can host up to 9 of them in there. It's about the size of an elevator. The 2 cabinets on the left and right hold the control electronics, and then behind there are the gas handling cabinets and connection to the connection to the cloud and things like that. Okay, so what I want to talk about today is quantum advantage. So this is our roadmap for quantum computing. It's quite detailed. It's on our website. I encourage you to go visit our website. You can check it out in detail. There's a lot of information there. Rather than go through the entire roadmap with you, let me draw your attention to 2, I think, important events. One is this year we think it's possible to demonstrate quantum advantage. It's not guaranteed, but it's a goal that we have. The second is that in 2029, we believe the first error-corrected quantum computer will be available. So let me talk about the first one. So the way we define quantum advantage is it has 2 parts. One, the output must be correct. There's no point in having a powerful computer when it's wrong. So first, the output must be validated. The second is that there must be some separation between the quantum and the classical. The calculation with a quantum computer must be somehow better than the computation without a quantum computer. It can be better in terms of accuracy, speed, cost. We think this year, most likely, accuracy is going to be the dimension in which advantage is demonstrated. But eventually, all 3 will be demonstrated because in computation, speed, accuracy, and cost are all connected together. Now, let me say that quantum advantage is not something that IBM will declare. We don't believe it's not a singular event that will happen on a single day. We believe that this is a consensus that needs to be achieved by the scientific community. The claim of quantum advantage is a scientific hypothesis. It can be falsified, or it can be supported. But only that can come about if a lot of people investigate it and come to agreement. So there have already been many papers who have claimed quantum advantage. And like I said, we don't believe that we can't declare quantum advantage. It's something the community has to come together and agree upon. So what we have done is we've set up a website to help facilitate this discussion. It's called the Advantage Tracker. Everybody's invited to come and post your claim of quantum advantage or your proof of that this is not quantum advantage. We invite both people in the IBM quantum ecosystem as well as people outside the quantum ecosystem. Both classical and quantum practitioners are welcome to participate and post. The main goal of this website is to give everybody an ability to make an equal comparison between computations. So quantum advantage is kind of a funny thing in that now we're at a point where we're claiming that we're doing a computation that is better than classical and therefore unverifiable by classical. So we see that there are 3 ways that quantum advantage may be claimed. The first one are methods that have provable confidence bounds. This is a kind of way to conduct a computation so that you do rigorous error propagation. The main kind of circuit that we see here are mirror circuits. As far as I'm aware, there's no practical application of that. I think the other 2 categories are where there's a lot of interest. The first is in chemistry, and the second is in optimization, and I'll talk about each of those in turn. But one take-home message here is that we believe that quantum advantage is most likely to be demonstrated in chemistry or in optimization with a higher probability in chemistry. So in chemistry, one way that quantum advantage could be demonstrated is through using algorithms with guaranteed solution bounds. These are algorithms that guarantee that their answer will always be above what we call the ground state energy. The GS stands for ground state. In chemistry, we're often looking for the ground state of a molecule or a material. Some methods can either overestimate or underestimate the ground state. The methods that we're citing here, the list over on the right, on the left, CI methods, DMRG, VQE, algorithms like that, these guarantee that any output from the calculation will always be above the ground state energy. It will never be below. And so you can compare the outputs of these algorithms by looking at simply who has the lowest energy. You know none of them can go below the ground state, and whoever has the lowest energy is the one closest to the ground state. So this is one way that one can demonstrate quantum advantage is by using these algorithms. So we have an example of that. This is work that we did with Boeing. This is a problem where you may know the 787, the new Boeing aircraft, has carbon fiber wings. The wings are subject to damage by UV radiation, which is particularly intense at the way up in the atmosphere. So this is the way the airline industry handles this problem is they paint the aircraft and the paint protects the carbon fiber material from the UV radiation. But this is a $300 million a year problem. You have to constantly repaint the aircraft. So what we're looking at here with Boeing is we're looking at how the UV damages, in particular, the epoxy molecules in the carbon fiber. You see the reactant, the transition state, and the product. TS stands for transition state. And then you can see the energies, the ground state energies that we calculate for each structure. You can see the orange point here is the extrapolated point, and the current best classical output is from a technique called DMRG, and we are within 1 to 2 millihartry of that. In other words, we're very close. We're almost at chemical accuracy with that. So one way to, and both of these methods, the quantum method is SQD, the classical method is DMRG. Both of these guarantee an upper bound to the energy output and will never go below the ground state. So whichever one is lower will be closer to the actual ground state. In this case, DMRG is slightly lower, and we see how to improve the quantum calculation to go beyond what DMRG can do, maybe as soon as the next couple of months. This is another example. This is another way to demonstrate quantum advantage will be to verify the output by an experiment. This is work that we did modeling hafnium oxide and zirconium oxide. These are important materials that are used for various applications such as corrosion protection. You can see in the upper orange bar, that is the quantum solution. The green and the blue bars are the classical solution. You can see that the quantum solutions in both cases are confirming experimental results. This is another example of confirmation by experiment. This is work that we did on modeling a magnetic material. In this case, we have two pictures, one on top and one on bottom. The one on top is the experiment. The one on bottom is the computer simulation. And what you see is what we're doing in the experiment is we're firing neutrons at a magnetic material and seeing how the neutrons change their energy and momentum. And that's plotted in the spectrum labeled delta E and momentum Q. We can do a similar simulation using a quantum computer. That's the bottom row. We use something called the Heisenberg model. We simulate this on a quantum computer. We calculate something called the correlator or the Green's function. And then you take that and you do a Fourier transform and you can recover the spectrum. You can see the outputs of the two calculations. On the top, in color, you can see the experiment. On bottom, in color, is the quantum calculation. You can see the two are quite similar qualitatively. Quantitatively, you can see some metrics that we posted on the far right. These metrics are statistical metrics, image comparison metrics, things like this. But you can see, again, we're getting quite close to using a quantum computer to predict experiment. This is another piece of work that we published about 2 months ago in April. Now we are using quantum computers to model very large molecules. In this case, we've modeled a 12,000 atom protein. The way we did this is we took the protein, we broke it up into many smaller parts. Each fragment we looked at, the smallest fragments we solved using a classical computer, the largest fragments we solved using a quantum computer, and then we use a classical computer to reintegrate all the pieces together. And we're able to calculate what's called the binding energy of a protein. You can see the two configurations of the protein here, the unfolded form and the folded form, and we calculate the difference in energy between those two forms. The other area where we believe quantum advantage is possible in the near term is optimization. This is, I think, lower probability than chemical and material simulation, but the probability is greater than 0. In this case, the way we verify the output is by simply comparing the solution from a quantum algorithm and the solution from a classical algorithm and see which one has the better solution. And in that case, the better solution will win. So, and what you see here is a plot of all possible solutions outputted by a quantum computer. All the way on the left, the high spike is the most optimal solution to an optimization problem. So in optimization, we have identified 3 regimes where quantum algorithms can play. The furthest right the furthest left is the provably exact algorithms. Those are algorithms that are guaranteed to find the global optimum. An example of that is Grover's algorithm. Grover's algorithm, though, requires a fault-tolerant quantum computer, so that is not going to be possible until 2029 at the earliest. The second column is provably approximate algorithms. These algorithms do not guarantee a global optimum, but what they do is that they'll guarantee a certain quality of solutions. So for example, in the max cut problem, there are algorithms that don't guarantee the global optimum, but what they do guarantee is that any answer that comes out will be at least 87% within the global optimum. And there are examples of quantum algorithms here. Probably the best known one is Google's decoded quantum interferometry paper that solves the polynomial intersection problem. As far as I know, no one has mapped that to an industrially interesting use case, but the mathematical framework has been established. The last column is your heuristic algorithm. Heuristic algorithms do not guarantee a global optimum, and furthermore, they don't guarantee a performance. But they tend to work pretty well in the classical space. The example we have is a traveling salesman problem. The traveling salesman problem is an NP-hard problem, but we have a heuristic that tends to take, that is pretty good. The largest traveling salesman problem would be a salesman visiting every city in the world. That's what this picture depicts. And the current state-of-the-art heuristic classical algorithm is able to find the solution to within 2% of the global optimum. It's already pretty good. So given the fact that classical heuristic algorithms work pretty well, there is a hope that quantum heuristic algorithms can also perform well on some problems. The question is which problems? Because these are heuristic, you don't know ahead of time which problems these algorithms will perform well on and which algorithms will not perform well on. So we published another paper, this intractable decathlon paper, and what we did is we benchmarked quantum algorithms against several problems, and we found several problems where the classical algorithm loses optimality within a fairly small size. So let me give you 2 examples. One is the Birkhoff minimum decomposition, and the other one is a portfolio optimization problem. In Birkhoff decomposition, this is work that we did with E.ON. E.ON is Europe's largest energy trading company. The energy landscape is getting more complicated now with the introduction of renewable energies. You have things like wind and solar that have intermittent and non-continuous output of energy. You also have things like electric vehicles, which can be both a source of energy as well as a sink of energy. And what E.ON would like to do is they would like to find point-to-point connections between sources and sinks. And that's exactly what the Birkhoff decomposition does. It takes a network like this, and it decomposes into a collection of point-to-point connections. So you see the point 1, the point 2, point 3, point 4. This network can be decomposed into those four point-to-point connections, and this allows E.ON to optimally figure out how to connect sources and sinks to each other in an energy grid. The last slide I have is for work that we do with Vanguard. This is in portfolio optimization. What we did here is we looked at a portfolio of 109 bonds, and each bond is either in the portfolio or out of the portfolio. So we have 2 to the 109 possible portfolios. That's about 10 to the 30 or 40 possible portfolios, so it's a very large number. What we did is we applied a quantum algorithm to optimize the portfolio. What we found is that the quantum algorithm was able to achieve within 2% of global optimality. Now the challenge with both of these algorithms is, and quantum optimization in general, is a way to scale them up to a point where classical algorithms start to fail. It's less true for Birkhoff decomposition. It's more true for Vanguard. If you look at our intractable decathlon paper, you'll see that classical optimizers tend to start failing around 700 binary decision variables, which corresponds to about 700 qubits. And there are we see a couple of ways forward in terms of being able to map that onto quantum computers. One is to simply wait for a quantum computer to have enough qubits, and we believe on our roadmap, we'll have 300 some qubits next year and 1,000 qubits the year after that, and so it's possible that we'll be able to demonstrate quantum advantage at that point. Another way to do it is to decompose the problem into smaller pieces that the quantum computer can handle. Okay, so that's my last slide. Is there any questions that I can take?